In the beginning, there was ignorance. The brain was without form, void of understanding, and darkness was upon the face of neuroscience. And lo, humankind did drill, prod, and poke, hoping to grasp the mysteries of the mind. But then, let there be light. And there was optogenetics. And we saw the light, and it was good. The age of crude tools had ended. No longer would we fumble in the abyss of uncertainty. With the power of light, we now command neurons, bending them to our will with divine precision. The darkness is vanquished, and a new era has dawned.
Okay, wow, that was a lot. Mankind did drill and poke, let there be light. Are you narrating a neuroscience pitch or rewriting the book of Genesis? Listen, I time traveled here respecting progress, and I see you're still stuck in the dark ages, literally. Trepanation, electrodes. What is this? 19th century brain hacking? Look, back in 2050, we don't worship optogenetics like it's some kind of divine miracle. We just use it. No grand proclamations, no sacred texts, just better science. So maybe instead of over the top theatrics, how about you just upgrade? Here to introduce you to optogenetics, the neural control technology of the future, available now. Optogenetics is all about precise control of cells using light. We're not just observing anymore, we're manipulating. The core idea, we introduce light-sensitive proteins called opsins into specific cells. These opsins, often derived from algae and archaea, act as light-activated switches. Channel rhodopsins like CHR2, activated by blue light, open and allow positive ions like sodium, potassium, and calcium to flow in, causing excitation. Halorhodopsins, on the other side, are activated by yellow light and pump chlorine ions into the cell, leading to inhibition. Archirhodopsins extrude hydrogen ions when stimulated by green-yellow light. Opsins are like tiny antennas installed on cells, allowing external light source to act as a remote control for their activity. And because we're using light, we can control these cells with incredible temporal precision, down to milliseconds. Why settle for outdated methods when optogenetics offers precision, self-time specificity, and reduced invasiveness? Unlike traditional electrical stimulation, like deep brain stimulation, which affects broad areas, optogenetics allows us to target specific cells within intact circuits without affecting surrounding tissues. Target only the cells you want, avoiding widespread effects like with drugs. You know another thing that drugs do? They take a long time to take effect. DREADS, or chemogenetics, offer a more targeted approach, but they rely on systematic drug administration, leading to slow onset and offset. Optogenetics, unlike DREADS, offer millisecond-level precision, enabling the accurate control of neuronal activity. We can turn cells on and off faster than a hummingbird's wings. This technique combines the spatial control of chemogenetic with the speed of electrical stimulation, all while avoiding the broad, systemic effect of drugs. But the future is even brighter. With optogenetics, we're not only controlling activity, but we're rewriting genetic expression. Light-inducible transcription factors, P-DON plasmids, and opto T7 RNAP allow precise activation and silencing of genes. And unlike electrodes, which can cause tissue damage and introduce artifacts, optogenetics relies on light, reducing mechanical disruption and offering greater stability over time. We are kinder to the surrounding tissues compared to sticking electrodes in there. By having excitatory and inhibitory opsins, we can both stimulate and suppress neural circuits. Not only that, but with engineered receptors, the same receptor can be both excitatory and inhibitory, depending on the wavelength with which it is stimulated. Having bidirectional control opens many possibilities, which is key for figuring out cause and effect in brain functions and disorders. To see what's going on in there, combine optogenetics with calcium imaging, electrophysiology, and MRI. You can correlate neural activity with behavior. This multimodal approach enhances understanding of circuit function in health and disease. But see what's happening in real time. Optogenetics isn't just about flipping neurons on and off. It's a precision tool for hacking the brain's code. Want to prove if a neuron controls behavior? Fire it up and watch the action, like triggering sleep on demand in Drosophila by activating dorsal fan-shaped neurons. Need to map circuits? Shine a light on a neural pathway and trace its connections, just like researchers did with fear circuits in the amygdala. But wait, there's more. Optogenetics isn't just a research toy, it's a revolution in treatments. Look, I know what you're thinking. Lab breakthrough, great. But does it actually work? Let me put it this way. We didn't just play with light in petri dishes. We took it to the clinic and, well, let's just say some pretty dramatic things happened. Parkinson's? We mapped those tangled circuits and flicked the right switches, restoring movement. Pain? Silence those screaming nociceptors with a pulse of light. Alzheimer's? We started untangling the mess, bringing back clarity. Epilepsy? Those chaotic storms? Tamed. Blindness? We rewired retinas, and yeah, people saw again. Diabetes, heart arrhythmia, you name it, the list goes on. We weren't just patching symptoms, we were fixing the root problems. So, yeah, it's gonna work, and it's gonna work pretty fast. But now, back to the science of your time. So let's address the elephant in the room. Optogenetics isn't perfect, but the challenges are being overcome faster than you can say temporal resolution. Skeptics argue that deep brain light delivery requires invasive implants. But what if we could achieve precise neurocontrol without surgery? Transcranial optical stimulation nanoparticles convert harmless, low energy light into precise wavelengths needed to activate those wonderful opsins deep within the brain. We simply shine this light on the scalp, and voila! The particles delivered intravenously act like miniature beacons, delivering light exactly where it's needed, non invasively. No surgery, no implants, just pure light based control. Minimal invasiveness with maximum control. Oh, and let's not forget the miniaturized wireless implants, no larger than a grain of rice. These biocompatible chips generate targeted wavelengths wirelessly powered by the body's own energy, allowing for personalized and adaptive treatment. Eliminating bulky equipment with these miniature marvels, we can truly unlock full potential of optogenetics. Anywhere, anytime. A key challenge of optogenetics is blue light's poor penetration. It's heavily scattered and absorbed in neural tissue, restricting its penetration to only the most superficial cortical layers. The solution? Red-shifted opsins for deeper reach with a minimal scattering. And that's not all. We're refining fiber optic implants, making them thinner, more efficient, and tailored for precise delivery. Soon, reaching deeper brain structures will be as simple as shining a flashlight into the night. I can almost hear what you are thinking about prolonged light exposure, especially at high intensities. Doesn't that risk photo damage and heat induced disruptions? Yes, it's true. Blast cells with too much light and their protest, much like humans in a sunbed for too long. But we're not reckless sunbathers here. We're far too meticulous for such reckless excess. But with optimized protocols, we keep protein loads checked and light levels finely calibrated, making autogenetics safer and more effective than ever. We don't even have to speak hypothetically. Restoring vision in retinitis pigmentosa with crimson R and combining optogenetics with a visual device for late stage retinal degeneration is possible. These clinical trials are happening and are already providing potential to optogenetics in humans, even at your time point. If we're already helping blind patients see again, do you really think we'll stop there? The road to human translation is paved with progress, not hesitation. So, how do we wield this power? Let's break it down. First, we need to get the light sensitive genes into the right cells. We do this by using viral vectors, tiny engineered delivery trucks designed to carry opsin genes straight to their target destinations. The adeno associated virus is our to go, efficiently delivering the genetic cargo to specific brain regions. Once inside, promoters, enhancers, and targeting sequences ensure that only the right cells activate, allowing us to precisely manipulate their function. It's like programming neurons with custom instructions. Next, the cell gets to work. Once the opsin genes are delivered, the cellular machinery kicks in, producing light sensitive proteins and embedding them right into the cell's membrane. Now, these neurons are primed and ready, waiting for the right signal to ignite. Time to flip the switch. After confirming successful option expression, we use implanted optical fibers to beam light of specific wavelengths deep into the brain. These fibers act like precision laser pointers, targeting neurons with millisecond accuracy. With spatiotemporal control, we dictate exactly when and where neurons fire, shaping brain activity like a conductor guiding an orchestra. Of course, we want to see what happens next. Using electrophysiology, calcium imaging, or even fMRI, we track neuronal responses in real time. We're not just activating cells, we're watching the brain react, adapt, change in ways that were once impossible to observe. But that's the beauty of optogenetics, not just control, precise, dynamic, and tunable control over the brain's electrical symphony. So, are you ready to join the optogenetics revolution? To unlock the secrets of the brain, develop revolutionary treatments, and push the boundaries of what's possible? Then get on board because in 2050, we're not just studying the brain, we're mastering it.
Optogenetics, the key to understanding and controlling the brain. Available now. Side effects may include paradigm shifts, Nobel Prizes, and the overwhelming feeling of scientific superiority.